With all the preliminaries out of the way, at last we're finally ready to look at the technique of partial fraction decomposition. Let's take an example integral we'd like to solve, the integral of 4x plus 8 over 2x squared minus 5x minus 3 dx. Notice that our integrand here is a proper rational function. That is, the degree on the top is 1, the degree on the bottom is 2. It means the degree on the top is less than the degree on the bottom. It's a proper rational function. So that's the kind of rational function that we can apply the technique of partial fraction decomposition to. Because the trouble is, we just don't know how to integrate this function right now. A u substitution is not going to be helpful. But we can break this integrand down as a sum of simpler rational functions that we can integrate. In particular, this technique is going to allow us to take this function, 4x plus 8 over 2x squared minus 5x minus 3. Just the function here. I'm taking it out of the context of the integral. But this function, we'll be able to break it down and write it as a sum of a simple rational function plus another one. The only question is what? Well, to start, we should start by factoring the denominator. So let's figure out how to factor it. On top is 4x plus 8 over what? Well, it turns out this will factor as 2x plus 1 times x minus 3. So here's our fact from algebra. This is a theorem that says that any proper rational function can be broken down uniquely in the following way. If the factors of the denominator are all linear factors, they have degree 1, and if they are all unique, there are no repeated factors, then we can break this down to the following. We'll have a rational function that has 2x plus 1 on the bottom, plus a rational function that has x minus 3 on the bottom. And furthermore, both of these will be proper rational functions, which means that the degree on the top of each one will be less than the degree of the bottom, which means that each one has to have a constant on the top. We don't know what those constants are, but we know that there's a unique set of constants that will work. So let's give these variable names. Let's call the one on top of 2x plus 1, let's call it a, and let's put b on the top of x minus 3. So our theorem says that there's a unique number a and a unique number b that makes this work, that this original rational function is equal to a over 2x plus 1 plus b over x minus 3. So if we can figure out what the a and b are, then we'll be able to insert this new version, this new expression that is equal to the original, into our integral and solve the integral very easily. We just need to figure out what a and b are. But we can now solve this algebraically. Now, if you look at this equation here, this is an equation, we should be able to solve it. You might look a little worried here because it's pretty complicated and there are a lot of variables. There's x and there's a and there's b in here. This is the very important thing to notice, is that our theorem says this equation is actually true for any possible value of x, which means x isn't really a variable in the traditional sense here. We actually can't solve for x. But because of that fact, it turns out even though we have only one equation, we will be able to solve for both a and b. So I'll show you how to do that in just a moment. Let's start by clearing our fractions here. I'd like to multiply both sides of the equation by 2x plus 1 times x minus 3. I can multiply the left and right-hand sides by those things. 2x plus 1 times x minus 3. Then I can cancel out the denominator entirely on the left and end up with 4x plus 8. And that equals, well, on the right, I need to distribute this entire product into both terms. But if I multiply 2x plus 1 times x minus 3 by a over 2x plus 1, well, those 2x plus 1s are going to cancel. I'll end up with a times x minus 3. plus, if I multiply b over x minus 3 times 2x plus 1 times x minus 3, the x minus 3's will cancel. I'll be left with b times 2x plus 1. So now we have a much simpler version of our equation. Now again, you have to keep in mind here, we are not trying to solve for x. In fact, we can't solve for x. In fact, this equation is true for every possible value of x. The variables that we're trying to solve for are a and b. But any value of x will still make this true. That means we can plug in any number we want for x, and we'll get an equation involving a and b that we can solve. So in particular, let's make a very clever choice of what number to plug in for x. I notice here that I have x minus 3 showing up in part of this equation. What if I could make that part go to 0? Let's try x equals 3. If I do that, the left-hand side will be 4 times 3 plus 8, and that equals a times 3 minus 3 plus b times 2 times 3 plus 1. So 4 times 3 plus 8, that is 20. And this equals, well, 3 times 3 is 0, so this whole thing is going to go to 0. 0 plus b times 2 times 3 plus 1, that is 7. So 20 equals b plus 7. We can solve for b here. That tells us b equals 20 over 7, that number right there. So now we've solved for b. Now let's try solving for a. It was really convenient to pick a number for x that caused the thing being multiplied by a to become 0. That meant that the a disappeared from our equation, we could solve for b. Now I'd like the b to disappear from my equation so I can easily solve for a. So perhaps I'll try and pick a number for x that causes 2x plus 1 to go to 0. That's easy. We'll just let x equal negative 1/2. So let's try that. 4 times negative 1/2 plus 8 equals a times negative 1/2 minus 3 plus b times 2 times negative 1/2 plus 1. Now 2 times negative 1/2 is negative 1, and we're adding 1, so this part is going to go to 0. So b times 0 is just 0. 4 times negative 1/2 is negative 2 plus 8, that is 6, and that equals a times negative 1/2 minus 3, that is negative 3.5, which is negative 7/2. And then plus 0, essentially. So if we solve for a is going to equal 6 times the reciprocal of that negative 7/2, which is negative 2/7, which is therefore negative 12 over 7. That is what a is. So we have successfully solved for both of these missing coefficients here, the numbers that appear on the tops of both of these simple rational functions. They both happen to be fractions. That's okay. Sometimes you get fractions, sometimes you get whole numbers, sometimes you get irrational numbers. That's all right. You're usually not going to get irrational numbers as long as the coefficients in your polynomials are rational, but that's not to worry about. Let's put these all back together here. We said that 4x plus 8 over 2x plus 1 times x minus 3 is equal to a over 2x plus 1 plus b over x minus 3. And we found that a equals negative 12 over 7, and b equals 20 over 7. So we can just fill these in now. That means that we have negative 12/7 over 2x plus 1. Make sure to emphasize your big division bar when you have a fraction over a fraction here. Plus, our b is 20/7 over x minus 3. Now, again, we have these compound fractions here. A lot of times, we would prefer to simplify these by moving these 7s down and be multiplied by the denominator and have just one fraction. But I don't think it's actually worth taking the trouble to do that this time around. Let's keep these as we are. So now let's go back to our integral. We're trying to find the integral, the indefinite integral of this rational function. So we can just rewrite our rational function in the form that we've now discovered for it. This equals the integral of negative 12/7 over 2x plus 1 plus 20/7 over x minus 3. All of that is times dx. Now, don't panic. There's lots of fractions here. But what we have really here is a sum of two expressions of the form a number over a linear function. We've already talked about how to integrate exactly these kinds of functions. It doesn't matter if the number on top is a fraction or an irrational number or what. It's just a number. So, for the first part here, that number on top is a coefficient that will go along for the ride, negative 12/7. Now, we could use a u substitution here. We could let our u be 2x plus 1, and we end up with a 1 over u. So the antiderivative will be the natural log of the absolute value of the bottom, which is 2x plus 1. But we've talked about how we need to handle a u substitution in this situation here. Because the u is a linear function of x, it's not very complicated, but you will end up having to divide by the coefficient on the x. So I'm going to divide by 2 or multiply by 1/2, and I'll clean up my coefficients later. Now, plus the next part. Again, we have this coefficient on the top here, 20/7. That just goes along for the ride, 20/7. And we've got a 1 over x minus 3. Now you could let your u in that case be x minus 3. You'd have 1 over u, and the antiderivative is the natural log of the absolute value of whatever the u is, x minus 3. And again, we have to divide by the coefficient on x, but the coefficient here is just 1, so there's no division to be done. We'll just add a constant. And as a final step, perhaps I will try to clean up my coefficients a little bit here. So this equals negative 12/7 times 1/2, that is negative 6/7, times the natural log of the absolute value of 2x plus 1, plus 20/7 times the natural log of the absolute value of x minus 3, plus a constant. I would say this is a quite sufficient simplified version of our answer. If you wanted to go a little further, what you could do is use laws of logarithms to take this, these coefficients in front of the natural log and bring them into the log as powers on the 2x plus 1 and on the x minus 3. You could also, if you really wanted to get wild, you could take the sum of these two logs here. Actually, it's a difference because the first one has a negative in front of it. And you could say, well, addition outside the log corresponds to multiplication inside the log, and you could write it as one big logarithm. I don't think it's worth the trouble of doing that, though. I think it's nicer to have a simpler argument in the log in exchange for a sum of several terms here. This is as simplified as we're going to get. So if you're looking at every single little step that we took, this can start to feel very complicated and overwhelming. But it's really not all that complicated. There's two basic things that we did. The first thing was to take this function right in here, our integrand, and rewrite it in an easier form, a form that is a sum of some simpler rational functions using the technique of partial fraction decomposition. So our first major step was to rewrite our function using algebra. And then the second step was simply to find the antiderivative of that new version of the function. And we've done that. It looks perhaps a bit complicated, but we know exactly where each of these terms came from. Drilling a little deeper, looking at this in more detail, that first step of partial fraction decomposition goes as follows. For partial fraction decomposition, you start with a proper rational function, so one that has a lower degree on the top than the degree of the bottom. And we'll break it down into a sum of terms that are simpler rational functions. Now, in our case, we only had a number over a number times x plus a number, like this. Later, we'll talk about what happens if you start bringing powers onto those bottom functions here. And we'll talk about what happens when you have an irreducible quadratic factor in your denominator. But for now, it's very simple. The point is we're going to break down that larger rational function into a sum of simpler ones. And how specifically do we do that? Well, we start with our proper rational function. We factored the denominator. Then we wrote out the expanded form. So we took each factor in the denominator. In our case, each factor was linear and they were unique. We only had one copy of each of those factors. In the expanded form, we just had a variable over the first factor plus a variable over the second factor. And if you had more factors, you would just have more variables over the additional factors. And we'll just use algebra to solve for those unknown coefficients, those variables that are on the top. So really, it's not a complicated process. There are a lot of steps if you try to look at them all at once, but if you focus on one part of the process at a time, then it's not too complicated. And we'll do more examples in the next few videos. And then, of course, your final step will be to bring that rewritten, that decomposed rational function back into the context of an integral. If you're trying to integrate the original rational function, you can now integrate the new, easier version, and you'll use all the usual techniques of integration that you have to solve that.